Professor Rajendra Singh, Raju Bhaiya, Institute of Physical Sciences for Study and Research, VBS, Purvanchal University, Jaunpur. Sir, we are thankful to you for accepting our request, and it is very important related with all the meteorologists, how to evaluate the uncertainty associated with the measurements. Thank you, sir. We have with us Shri B.N. Dikshit sir. Sir, Shri Dikshit sir. Shri B.N. Dikshit sir. Santosh ji, I think he is not able to listen me. Santosh ji, am I audible?
Yes, sir. Yes, sir. Very much audible, sir.
Will you please speak to Dikshit sir? I think his mic is off.
I think my mic is unmuted. Please continue, sir.
Okay. Dikshit sir. Professor Devraj Singh. Sir, am I audible to you?
Hello.
Yes, sir. Devraj, sir. Yes, you are audible, sir.
Is it? Is there some problem? Professor Devraj Singh, I'm not able to hear you. Santoshi, will you please speak to him?
Devraj, sir. Am I audible, sir?
Are you?
Yes, sir. Sir, your voice is breaking. Professor Devraj Singh. Santoshi, will you please speak to him?
To Mr. Ashutosh Agarwal for inviting me
Yeah.
to deliver my
Thank you,
talk
sir.
on this national workshop seminar on evaluation of uncertainty associated with measurements. I am Professor Devraj Singh. I am here at Veer University Department since 2020. This is a very important topic for the meteorologists. As you know, one of our meteorologists, William Thompson, said, when you can measure what you are speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meagre and unsatisfactory kind. Another two scientists published one of the paper in Deputy Journal. They wrote, whenever standards are used for testing measuring instruments, they must be traceable to national or international standard. When the instrument have been calibrated, the measurement uncertainty is normally given on the certificate. If, however, the measuring instruments have been verified, the measurement uncertainty is not always quoted. This may be due to the maximum permissible error. So now, first question: What is measurement? Measurement tells us about a
Sorry, his connection has been lost. He will join again. Wait for 2 minutes. Devran sir, please join. Please start your PPT, sir.
हेलो संतोष जी। हेलो।
Yes, sir. दीक्षित सर
आई
बोलिए
एम
सर.
ऑडिबल ना?
हेलो।
Yes, sir.
हाँ हाँ, मैं कर रहा हूँ। वो 1 मिनट वो जोड़ने लगा था ना दूसरे से।
सर आपका वॉइस ब्रेक हो गया था बीच में.
हाँ हाँ, ठीक।
हेलो. हेलो.
हाँ, दिख रहा है।
यस सर, दिख रहा है. बट सर दिस इज द ओनली सेकंड स्लाइड. या इट इज अनशेयर्ड नाउ. संतोष जी, ये व्हाट इज द प्रॉब्लम?
I think his screen is unshared.
नाउ यस.
तो
या
हाँ, कर रहा हूँ। आ गया। ठीक है सर, मैं थोड़ा सा जल्दी करूंगा क्योंकि इंटरनेट चल नहीं रहा है और मोबाइल से ही जोड़े हुए हैं।
Sir, Devran sir, continue.
स्टार्ट करूं?
Next slide.
हेलो, वेरी गुड मॉर्निंग। My internet is very slow. हेलो।
हाँ सर, आपकी नेक्स्ट स्लाइड कीजिए ना अभी सर. अभी सेकंड स्लाइड आया है, नेक्स्ट लीजिए अभी.
यहाँ से बोलना है।
हाँ बोल.
ठीक।
Yes sir, measurement से start कीजिए सर. Yes sir.
Measurement tells us about the property of. Tell us how heavy an object is or how hot it is. A measurement gives a numbers to that property. Measurement are always made of some kind, like rulers, stopwatches, uh, elbow rulers, calipers, micrometer, stopwatch, thermometer, angle ruler, roll meter, etc. Result of measurement is normally in two, and then its unit. Example: how is anything? It is 2 is the number and meter is unit. What are not a measurement? What is not a measurement? There are some processes that might measurement but are not. For example, spring to see which is longer is not really measurement. Counting is not normally viewed as a measurement. Often a test is not a measurement. Tests normally lead to a yes or no. Either it is long or short. However, measurement of the process leading up to a test result. Now, second question is what is the uncertainty of measurement? Measurement tells us something about its quality. Is a doubt that exists about the result of any measurement. Anyone might think that well-made ruler, thermometer, etc. should be or give the reason. For every measurement, even the most careful, there is always in every speech. This might be expressed as give or take. A stick might be 2 meter long, give or take a centimeter. Now, question is why we need uncertainty. So the evaluating the significance of quality management of companies throughout the world have had their quality systems ISO 9000 series of standard. As a rule, the quantities to be measured are traceable to SI unit in an unbroken chain of comparison measurements carried out by the statement of measurement with reference to standard use is an essential part of every calibration. Use of legally verified instrument for this purpose sometimes present problems, since although the maximum permissible error for the instrument are known, no measurement uncertainty explicitly given. There is some history about the uncertainty. The unit of mass, volume, and length are the commercial actions. Their measurement determines the price, cost, various interest, as well as regional and historical difference lead to differing units and systems. In cross-border trade, in segments, pressure, growth, or harmonization, this results in the SI system, which not only become the legal basis for the official dealing and but also gain in importance in the non-regulatory field of industry metrology. An efficient metrology infrastructure is the basis of all modern industrial societies, and from this point of view, legal metrology must be pioneer of uniformity. Main objective of legal metrology is to protect citizens against the consequences of false measurement in official dealing and commercial transactions, as well as in labor, health, and environment area. As the interest of the measurement areas differ, the instrument used will be satisfactorily controlled by market forces. Legislation therefore lays down requirement not only for measuring instrument but also for the measuring and testing methods. Everyone concerned with the measurement should have instruments which give correct specified some permissible errors under the local environment conditions. As the parties concerned by the measurement are not normally metrological, and do not have capability of checking the result. They are given state therefore responsibility for the validity of measurement within the framework of legal methodology. Now, contribution to the use and the standard use, the measuring will be used, the measuring methods, correct measuring methods, environmental conditions, susceptibility to interference, the state of the object to be measured or calibrated, and the person performing the measurement or calibration. Now, expressing uncertainty of measurement. There is always a mark of doubt. As I previous slide, any measurement we need to ask how big and how bad is the doubt. Some said when we are in doubt whether an action is good or bad, abstain from it. Thus, two numbers are really needed in order to quantify and uncertainty. One is the of margin, other is confidence level, and it states how sure we are that the true value is within that margin. For example, we might say that the length of a certain stick measured 20 centimeters plus or minus 1. That is the 9% confidence level. This result could be written as 20 centimeter plus minus 1 centimeter at the level of confidence 95%. We are 95% sure that the stick is between centimeter and 21 centimeter long. There are other ways to state confidence level. Now, error versus uncertainty. It is important not to confuse the term error and uncertainty. Error is nothing but it is the difference between the measured value and the true value of the things being measured, while uncertainty is a quantification of the doubt about the measurement result. Whenever possible, we try to correct for any non-error. For example, while applying the correction from the calibration certificate, but any error whose values we do not know is a source of uncertainty. Now, importance of uncertainty of measurement. Anyone may be interested in uncertainty of measurement simply because he wishes to make good quality measurement and to understand the results. However, there are other for thinking of measurement uncertainty. Anyone may be making the measurement. Here, the uncertainty of measurement must be reported on certificate. Second is the uncertainty of measurement needed to determine the fail or to make a tolerance. Here, anyone needs to know
Excuse me, sir. Slides are not moving.
he or she decides
संतोष जी,
whether
slides move नहीं कर रही हैं. Please check.
or
Sir, slides are not moving.
and understand a calibration or rating specification for a test or measurement.
संतोष जी,
Basic statistics on sets of numbers. Major
Hello.
price cut once.
hello, hello, hello,
There is a saying among
Hello.
craftsmen. Major price cut once, which means use the risk of making a mistake in bulk by
संतोष जी,
using the measurement
संतोष जी,
a second or third time
संतोष जी,
before he or she proceeds.
प्रोफेसर साहब,
That it is wise to make the measurement at least 3 times. Making only one measurement means that a mistake
Santoshi.
could go completely unnoticed.
संतोष
If
जी,
anyone makes they do not agree,
Yes, sir.
he or
Yes, sir.
she still may not know
Yes, sir.
wrong, but if they make three measurement and two agree with each other, while the third is very different, then they could be suspicious about the third. Simply to guard against gross mistakes, our operator tries to make a strict price at any measurements, but uncertainty of measurement of operator. There are other good reasons for the repeating measurements many times. Basic statistical calculation. One increase the amount of information measurement by taking a number of reading and carrying out some basic statistical calculation. The two most important statistical calculation are to find the arithmetic mean and the standard number. Getting the best estimate, taking the average of the number of reading. If repeated measurement gives the correct answer, one may not be doing anything wrong. It may be due to natural variations in what is going on. For example, if you measure a wind speed outdoors, it, it will not often have a speed, or it may be uh, because your measuring instrument does not behave in a completely stable way. For example, tape measures uh, may stretch and give different results. Variation in readings when they are repeated, it is the best. हेलो स्लाइड इसमें तो चल रही है
सर स्लाइड मूव नहीं हो रहा है आपका.
अच्छा अच्छा एक मिनट
अभी आप नेक्स्ट कीजिए.
हाँ हाँ ये इसको हाँ हाँ पीपीटी हाँ ऐसे चलने दें अभी आ रही है हाँ ठीक है मैं वो तो मैं कर लूँगा ऐसे चलते जाए ना ठीक है if there is variation in reading when they are repeated it is best to take many readings and take an average. Average give you an estimate the true value. Hello इसको ये वाली मैंने हटा दी और पॉइंट आ रहा है आ रहा है
यस सर आ रहा है
अच्छा ठीक
सर आ रहा है सर. वी आर एबल टू सी.
an average or arithmetic mean is usually shown by the symbol with a bar above it. For example, x bar is the mean value of the x. Following figure shows an illustration of a set of values. Suppose there are number of values are given here. Suppose 10 values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Following example shows how the calculation and arithmetic mean. Taking the average or arithmetic mean of a number of values, a set of 10 results. To find the average, add them together and divide by the number of values. For example, these values are given 16, 19, and so on, 13. And we get 170, we divide by the 10, we get the average 70. How many readings should you average? Now question is, how many readings will be chosen? Totally speaking, the more measurement anyone use, the better estimate will be the true value. The ideal would be to find the mean from an infinite set of values. The more result anyone uses, the closer you get to the ideal estimate of the mean. But performing more reading takes extra effort and is in return. What is a good number? 10 is a popular choice because it makes the arithmetic easy. Using 20 would only give a slightly better estimate, and 10 using 50 would be only slightly better than 20. As a result of thumb, usually between the 4 and 40. Next is spread standard deviation and repeated measurement give different results. We want to know how widely spread the reading are. The spread of the value tells us something of the measurement. By knowing how large is spread is, anyone can begin to judge the quality of the measurement or the set of measurement. Sometimes it is enough to know the range between the highest and lowest values, but for a small set of values, this may not give useful information about the spread of the reading in between the highest and lowest. For example, a large spread could arise because reading is different from other. The usual way to quantify spread is standard deviation. Standard deviation of a set of a number tells us about how different the individual readings typically are from the average of the set. As a thumb rule, roughly two-thirds of all readings will fall between plus or minus one standard deviation of the average. Roughly 95% of all readings will fall within two standard deviations. This rule applies widely, although it is by no means universal. True value for the standard deviation can only be found from a very large set of readings from a moderate number of values. Only a standard deviation can be found. The symbol S is usually used for the estimated standard deviation. For example, calculating an estimated standard deviation, uh, we take example from a book. It is rarely convenient to listen by hand with pen and paper. Because you have of readings, or a set of readings, we use 16, 19, 18, 17, 19, 20, and so on. Average is 70 as we discussed in previous slide. Next, find the difference between the readings. We see here the difference plus 2, plus 3, minus 2, minus 4. Then square it. And next, find the total divided by these readings are 10. We divide by 9, we have this number. Then we take we will take the square root of it. The complete process of calculating estimated standard deviation for a series of n measurements can be expressed mathematically using this formula of a standard deviation. Here, xi is the result of ith measurement and x bar is the arithmetic mean of n results. Calculator tips. Usually easiest to use the function key on the calculator to find the estimated standard deviation. Enter the reading into the calculator memory according to instruction for a storage of calculator. Then use the estimated standard deviation key S or sigma. How many readings do you need to find an estimated standard deviation? Again, the more reading you use, the estimate will be. In this case, it is the estimate of uncertainty that improved with the number of readings, not the estimate of mean or individual. Thorough estimate the result should be adjusted to take into account the number of readings. Where do errors and uncertainty come from? Many things can undermine a measurement. In the measurement may be visible or invisible because real measurements are never made under uncertainty can come from the measuring instrument. The instrument can suffer from error including noise, changes due to the aging, wear, or other kind of drift, poor readability, noise, or electrical instrument, and many other problems. The item being measured may not be sterile. An agent trying to measure the size of ice cube in a warm room. Possible? Is that correctly? The measurement process, the measurement itself may be difficult to make. For example, measuring the weight of a small but lively and lively animals present particular difficult to operate. Imported uncertainties. Calibration of your instrument has an uncertainty. This is uh, then built into the uncertainty of the measurement and the make. But remember that the not rating first. Operator is key. Also, problem some measurement depends on the skill and judgment of the operator. Person may be better than the another. And the delicate work of setting up the measurement or at reading fine detail by eye. The use of an instrument such as stopwatch depend on the reaction time of an operator. But loss mistakes are the different matter and are not to be accounted for. Next is sampling issue. Measurement you made must be properly representative of the process you are trying to access. If you want to know the temperature at the workbench, don't measure it with the thermometer placed on the wall. Here an air condition outlet, if anyone is switching sample from the production line for the measurement, don't always take the first 10 minutes on the any morning. Next is environment, temperature, air pressure, humidity, and many other conditions can affect the measuring instrument or the item being measured. Then the size and effect of an error are known from the calibration certificate. A correction can be applied to the measurement result, but the internal uncertainty from each of these sources and from other sources to the individual input contributing to overall uncertainty in the measurement. General kind of uncertainty in any measurement. The effect can give rise to uncertainty in measurement can be either random or static. Random, where repeating the measurement gives a randomly different result. If so, the more measurement you make and then average, the better estimate you generally can expect to get. Systematic, let the same influence affect the result for each of the repeated measurement, but anyone may not be able to tell. In this case, you learn nothing extra just by repeating measurement. Other methods are needed to estimate uncertainty with systematic effect. For example, different measurement or calculation. Now, distribution, the shape of the error. Spread of a set of values can take different form or probability distribution. Normal distribution, this is Gaussian distribution in a set of reading. Sometimes the values are more likely to fall near the average than further away. This is typical of a normal or Gaussian distribution. You might see this type of distribution if anyone examines the height of individual in a large group of men. Most of men close to the average height, you are extremely tall or short. Figure 2 shows a set of 10 random values in a approximately normal distribution. A stage of normal distribution may be done by the figure 3. Uniform or rectangular distribution, when a measurement are quite eventually quite evenly spread with values, a rectangular or uniform distribution is produced. This could be seen if you examine how raindrops fall on a thin straight telephone wire. For example, they would be likely to fall on any one part as on another. Figure 4 shows a set of 10 random values in an approximately rectangular distribution. A sketch of rectangular distribution is shown in figure 5. What is not a measurement uncertainty? Mistakes made by the operator are not measurement. They should not be counted as contributing uncertainty. They should be avoided by working carefully, by checking work. Tolerance are not uncertainty. They are acceptance limit, which are choosing for process or a product. About the compliance with the specification will be discussed. Guys, specifications are not uncertainty. A specification tells anyone what he or she can expect from the product. It may be very wide ranging, including non-technical quantities, the qualities of the item such as its appearance, accuracy, or rather inaccuracy. It's not the same as uncertainty. And unfortunately, usage of these words is often confused. Accuracy is a qualitative say, we say that the measurement was accurate or non-accurate. Uncertainty is quantitative. When a plus or minus figure is quoted, it may be called an uncertainty but not an accuracy. Error. Error are not same as uncertainty. Even though it has been common in the past to use the word interchangeable in phrases like error analysis. Statistical analysis is not same as uncertainty analysis. Statistics can be used to draw all kind of conclusions which do not by themselves tell us anything about uncertainty. Uncertainty analysis is uh, only one of the uses of the statistics. How to calculate uncertainty of measurement? Calculate the uncertainty of measurement. First, anyone must identify the sources of uncertainty in measurement. Then he or she must estimate the size of uncertainty from each source. Finally, the individual uncertainty are combined to give an overall figure. These are clear rules for the assessing the contribution from each uncertainty and for combining these together. The two ways to estimate uncertainties. No matter what are the sources of the uncertainty, there are two approaches to estimate them, type 1 and type 2 evaluation. In most measurement situation uncertainty, evaluations of both type are valid. Type 1 evaluations uh, uncertainty estimate using the statistics, usually from repeated readings. Type 2 evaluation uncertainty estimate from any other information, which could be information from past experience of the measurement or from calibration certificate, manufacturer's specifications, and from calculation from published information and from common sense. There is a temptation to think of type A as random and type B as systematic. But this is not necessarily true. How to use the information from type A and type B evaluations is described below. Uh, uh, 9 main steps to evaluating uncertainty. The main steps are the following. Decide what he or she find from the measurement. Decide what actual measurement and calculation are needed to produce the final result. Carry out the measurement needed. Estimate the uncertainty of each input quantity that feeds into the final result. Express all uncertainty in similar terms. Decide whether the error of the input quantities are independent of each other. If anyone thinks not, then some extra calculation or information are needed. Calculate the result of your measurement, including any non-corrections for the things such as calibration. Find the combined standard uncertainty from all individual aspects. Express the uncertainty in terms of coverage factor together with the size of the uncertainty interval and state a level of confidence. Write down the measurement result and uncertainty and state how you got both of these. This is general outline of the process and example where the steps are carried out with giving in the further. Other things he or she know before making an uncertainty calculation. Uncertainty contributions must be expressed in singular terms before they are combined. Thus, all the uncertainty must be given in the same units and at the same level of confidence. Standard uncertainty, all the contributing uncertainties should be expressed at the same confidence level by converting them into standard uncertainties. A standard uncertainty is a margin whose size can be thought of as plus or minus 1 standard deviation, the standard uncertainty tell us about the uncertainty of an average, not just about the spread of value. A standard uncertainty is usually shown by the symbol U or UY as standard uncertainty in the values of Y. Calculating a standard uncertainty for a type A calculation that is random. When a set of several repeated readings has been taken for a type A estimate of uncertainty, mean X bar and estimate standard deviation S can be calculated for a set. From these, the estimated standard uncertainty U of the mean is calculated from this formula U equal to S divided by under root N. Where N is the number of measurement in the set. The standard uncertainty means has historical also been called standard deviation of the mean or standard error of the mean. Calculating standard uncertainty of a type B evaluation that is systematic where the information is more scarce. In some type B estimate, he or she might only be able to estimate the upper and lower limits of uncertainty. You may then have to assume the value is equally likely to fall anywhere in between. A rectangular or uniform distribution, the standard uncertainty for a rectangular distribution is found A divided by root 3. Here A is the semi-range or half bits between the upper and lower mean. Rectangular or uniform distribution occur fairly commonly, but if you have good reason to expect some other distribution, then you should base your calculation on that. For example, he or she can usually assume that uncertainty imported from the calibration certificate or a measuring instrument are commonly converting uncertainty from one unit of the measurement to the another. Uncertainty contribution must be in the same unit before they are combined. As the saying goes, he or she cannot compare apple with pears. For example, in making the measurement of length, measurement uncertainty will be eventually be stated in terms of length. One source of uncertainty might be the variation in room temperature. Although the source of this uncertainty is temperature, the effect is in terms of length and it must be accounted for in units of length. You might know that the material being measured expand in the length by 0.1% for every degree rise in temperature. That case, a temperature uncertainty of plus minus 2 degrees centigrade would give a length uncertainty of plus minus 0.2 centimeter in a piece of material of 100 centimeter long. Once the standard uncertainty are expressed in consistent unit, the combined uncertainty can be found using one of the following techniques. Combining standard uncertainty. Individual standard uncertainty calculated by type A or type B values can be combined validly by the summation in quadrature as known as sum of the squares. The result of this is called the combined standard uncertainty, generally denoted by UC or UCY. Summation in quadrature plus where the result of the measurement is reached by addition or subtraction. The more complicated cases are also covered below for the multiplication and division of measurement as well as for other functions. Summation in quadrature for addition and subtraction. The simplest case is where the result is the sum of a series of measured values either added together or subtracted. For example, you might need find the total length of a fence made up of different widths fence panel if standard uncertainty in meter in the length of each fence panel was given by A, B, C, etc. Then the combined standard uncertainty meter for the whole fence will be found by the squaring the uncertainty, adding them together, and taking the square root of the total as we discussed in before. Combined uncertainty will be under root of a square plus b square plus c square and so on. Summation in a quadrature or multiplication of division. This is also interesting. For more complicated cases, it can be useful to work in terms of relative or fractional uncertainty to simplify the calculation. For example, you might need to find the area of a rectangular carpet by multiplying by the length and width by width. W A will be equal to length multiplied by the width. The relative or fractional uncertainty in the area of carpet can be found from the fractional uncertainties the length or and width. For length, the uncertainty is UL and relative uncertainty will be UL divided by L. For width, relative uncertainty will be UW divided by W. Then the relative uncertainty in area. So A divided by A will be given by this formula equation 5 UA divided by A and UL divided by N whole square plus UW divided by 2 whole square divided under root. For a case where the result is found by multiplying three factors together, equation 5 would have three such terms. For finding the suppose we want to find the volume of anything, length, uh, width, and height, then we will take the uncertainty in the volume will be uh, 2b divided by b, ul divided by n whole square plus uw divided by w square plus u h divided by h within under root. So we will get for the more than two terms. Equation can also be used directly for a case where the result is quotient of two values, one number divided by another. For example is given. Summation of quadrature for more complicated function. Here a value is square. The calculation of the final measurement result, then the relative uncertainty due to squared component is the form of this. 2 z divided by b. Here a square root value will be is a part of calculation of result, then the remaining uncertainty due to that component is the form of uz divided by 2z. In case of z square, this will be double. Relative uncertainty will be double, and while in case of square root, the relative uncertainty will be half. Of course, some measurements are processed in formally, which use the combination of addition, subtraction, multiplication, and division. For example, anyone might measure the electrical resistance and voltage and calculate the resulting power using the relationship E equal to B square upon R. In this case, the relative uncertainty of power UP divided by P and the value of power would be given by UP divided by P. This will be U B divided by B whole square and UR divided by R. Relative uncertainty of the relative uncertainty of the voltage and resistance within the under root square root. Generally speaking, for multi-step calculation, process of combination of standard uncertainty in the quadrature can also be done in multiple steps using the relevant form for addition, multiplication at each step. Combination of the quantities are discussed in many books. Now, correlation, the equation given above slides to calculate the combined standard uncertainty are only correct if the input standard uncertainty are not interrelated or correlating. Which means we usually need to question whether all the uncertainty contributions are independent. Put a large error in one input cause a large error in another. Put some outside influence such as temperature have similar effect on several aspects of uncertainty at once, individually or individually. Often individual errors are independent, but if they are not extra calculation are needed. Next one thing, important thing is coverage factor K. Having scaled the component of uncertainty consistently to find the combined standard uncertainty anyone needs, then want to rescale the result, the combined standard uncertainty may be thought of as equivalent to one standard deviation. But we may wish to have an overall uncertainty stated at another level of confidence, for example, 95%. Rescaling can be done using the coverage factor K multiplying the combined standard uncertainty UT by a coverage factor gives the result which is called the expanded uncertainty, generally denoted by capital U. A particular value of coverage factor or factor gives a particular confidence level of the expanded uncertainty. Most commonly, anyone scale the overall uncertainty by using a coverage factor K equal to 2. Keep the level of confidence approximately 95%. K equal to 2 is correct if the combined standard uncertainty is normally distributed. This is usually a fair assumption, but reasoning behind this is explained elsewhere. Hence, reasoning about this is given in some books. Now, the coverage factor for the normal distribution are when coverage factor K equal to 1 for a confidence level of approximately 68%. Coverage factor 2.58 for the confidence level of 99%. And coverage factor K equal to 3 for a confidence level of 99.7%. Other less common shapes of distribution have different coverage factors. Conversely, Wherever an expanded uncertainty is quoted with a given coverage factor, anyone can find the standard uncertainty by the reverse process, that is, by dividing by the appropriate coverage factor. This is the basis for the finding the combined standard uncertainty as shown in further slides. This means that the expanded uncertainty given on the calibration certificate, properly expressed, can be decoded into standard uncertainty. How to express the answer? It is important to express the answer so that anyone can use the information. The main things to mention here, the measurement result together with the uncertainty figure. For example, the length of the stick was 20 centimeter plus minus 1 centimeter. The statement of the coverage factor and level of confidence, the recommended wording is quoted uncertainty based on the standard uncertainty multiplied by the coverage factor k equal to 2, providing a level of confidence of approximately 95%. A basic calculation of uncertainty. Below is a work example of a simple uncertainty analysis. It is not realistic in the every detail, but it is meant to be simple and clear enough to illustrate the method. First, the measurement and analysis of uncertainty are described. Secondly, the uncertainty analysis is shown in a table, spreadsheet model for uncertainty budget. The measurement, how long is a piece of string? Suppose you need to make careful estimate of length of a piece of string. Following step listed in previous slide, the process is as follows. Calculating the uncertainty in length of a piece of string. Step 1. Decide what you need to find out from your measurement. Decide what actual measurement and calculation are needed to produce the final result. Anyone needs to make the measurement of length using a tape meter. Apart from actual length, reading on a tape meter, he or she may need to consider possible error, possible error of the tape measure. Does it need any correction or has calibrations on it to read correctly, and what is uncertainty in the calibration? Is the tape prone to stretching? Would bending having shortened it? How much could it have changed since it is calibrated? What is the resolution? How small are the division on the tape? For example, in millimeter. Possible error item being measured. Does the string lie straight? Is it under or over straight? Does the prevailing temperature, humidity, anything else affect actual length? Are the ends of the string well defined or they frayed? Possible error due to the measuring process and person making the measurement. How well can any line up the beginning of the string with the beginning of the tape measure? Can the tape be laid properly parallel with the string? How repeatable is the measurement? Can anyone think of any others? Step 2. Carry out the measurement needed. Anyone make and record the measurement of length? Be extra thorough. You repeat the measurement at a total 10 times or 20 times, aligning the tape measure precisely each time. Let us suppose the calculate the mean of mean to be 5.017 meter and the estimated standard deviation to be 0.001 meter, 0.1 millimeter. For careful measurement, you might also record when anyone did it, how anyone did it, along the ground or vertically reversing the determined measure or not, and other details of how he or she aligned the tape with the stem. Which tape measure you need environmental condition? If anyone think could affect your result. Step 3. Estimate uncertainty of each input quantity that feeds into the final results. Express all uncertainty in similar terms. Standard uncertainty U. Anyone would look at all possible sources of uncertainty and estimate the magnitude of each. Let us say that in this case, the tape measures has been calibrated. Let us suppose we calculate how anyone did it along the ground or vertically reversing the tape, measure or not, and other detail. He or she aligned the tape with the string. Which tape measure you use in environmental condition? If anyone think these could affect your result, anyone else that could be relevant. So, step 3, estimate the uncertainty of each input quantity that feeds into the final result. Express all uncertainty in the items. Anyone would look at all possible sources of uncertainty and estimate the magnitude of each. Let us say that in this case, the tape measure has been calibrated if needs no correction, but calibration uncertainty is 0.1% of reading at the coverage factor, and for normal distribution in this case 0.1% of 5.017 meter is close to 5 millimeter. Dividing by 2 is standard uncertainty. For k equal to 1, its u will be equal to 2.5 millimeter. The division on the tape on millimeter reading the nearest division gives the error of no more than 0.5 millimeter. He or she can take this to be uniform distribution. Distributed uncertainty, the true reading could lie nearestly anywhere in the 1 millimeter interval. Find the standard uncertainty he or she divide the half width 0.5 millimeter divided by under root 3 as the formula A divided by under root 3, you will get the standard uncertainty 0.3 millimeter approximately. It lies straight, but let us suppose this thing unavoidably, unavoidably has a few slight bend in it. Therefore, the measurement is likely to underestimate the actual length of this thing. Let us guess that the underestimate is about 0.2% and that the uncertainty in this is 0.2% at most. This means we would correct the result by adding 0.2%, and that is 10 centimeter. The uncertainty is assumed to be uniformly distributed in the absence of better information. Dividing the half bit uncertainty by under root 3 by the simple formula A divided by under root 3, we get the answer standard uncertainty 5.8 millimeter. Among all our type B estimate below a type A estimate, the standard deviation tells us about how repeatable the placement of the tape measure is and how much the contribution to the uncertainty of the mean value. The estimated standard deviation of mean of 10 reading is found using this formula s equal to 1107 millimeter. Let us suppose that no other uncertainty need to be counted in the example. In reality, other things would probably need to be included. Therefore, decide whether the error of input quantity are independent of each other. If anyone thinks not, then some extra calculation or information are needed. In this case, let us say that they are all independent. Step 5. Calculate the result of your measurement, including any known correction for the things such as calibration. The results come from the mean reading, together with the correction needed for this thing lying slightly lean. So this here may be written as 5.017 meter plus minus 0.01 meter, so it will be 5.027 meter. Find the combined standard uncertainty from all the individual aspects. The only calculation used in finding the result was adding of the correction to some of the quadrature and used in the simplest form. The standard deviation and combined standard deviation is under root because values are 2.5, 0.3, 5.8 and 0.7. We square all these and adding them and we take the square root of this one decimal place. Step 7. Express the uncertainty in terms of coverage factor. Together with the size of uncertainty, interval and state of real confidence. For a coverage factor k equal to 2, multiply the combined standard uncertainty to give the expanded uncertainty of 12.8. This gives a level of confidence 95%. Write down the measurement result and uncertainty, state how you got both of them. Suppose he or she might record the length of the string was 5.027 millimeter plus minus 0.013 meter. The reported expanded uncertainty is based on the standard uncertainty multiply the coverage factor equal to 2, providing the level of confidence of approximately 95%. The reported length is the mean of 10 repeated measurement of the string laid horizontally. Result is corrected for the estimated effect of the string not laying completely straight when measured. Now, analysis, as we discussed in previous slides, analysis of uncertainty on a spreadsheet. To help in the process of calculation, it can be useful to summarize the uncertainty analysis or uncertainty budget in the spreadsheet as shown in this table. These are source of uncertainty like calibration, resolution, string not lying perfectly straight, standard uncertainty of obtained repeated reading, etc. So we put all these things on the spreadsheet. Probability distribution, either it is normal or rectangular, probability of alternate. Other statements compliance with the specification. When the conclusion are drawn from the measurement results, the uncertainty of the measurement must not be forgotten. This is particularly important when the measurements are used to test whether or not a specification has been made. Sometimes a result may fall clearly uh, inside the inside or outside the limit of the specification, but uncertainty may be overlap the limit or kind of these are this one and this one, this one and this one. So we can see the four cases how the measurement result is a limit of a standard specification. Similarly, and uncertainty may overlap the lower limit of the specification. So we can say, see the case one, both the result and uncertainty inside the specified limit. This is closed as compliance. In case D, neither the result nor any part of the uncertainty will fall within the specified limit. So this is uh, classed as a non-compliance. It will be in compliance and this will not be in not compliance. And other two cases are neither completely inside nor outside the limit, so no firm conclusion about about them can be made for the B and C. Before stating compliance with the specification, I will set the specification. Sometime a specification cover various properties such as appearance, electrical connection, interchangeability, which have nothing to do what has measured. How to reduce uncertainty in measurement? Always remember that it is usually as important to minimize uncertainty as it is to quantify them. There are some good practices which can help to reduce uncertainty in making measurement. Generally, a few recommendations are the following: calibrate measuring instrument or have them calibrated for you and use the calibration correction which are given on the certificate. Make corrections to compensate or any other errors you know about. Make your measurement traceable to national standard by using a calibration which can be traced to national standard by an unbroken chain of measurement. He or she can place particular confidence in the measurement traceability if the measurement are quality assured through a measurement accreditation. Choose the best measuring instrument and use calibration facility with the smallest uncertainty. Take measurements by repeating them or by getting someone else to repeat them from time to time. Or use the other kind of checks. Checking by different method may be best upon. Check calculations and where number are copied from one place to another. Check this too. Use an uncertainty budget to identify the worst uncertainty and address them in a spreadsheet. Be aware that in a successive chain of calibration, the uncertainty increases at every step of chain. Some other good measurement practices. Overall, use recognized good practices in the measurement. For example, follow the maker's instruction or using maintaining instrument. Use experienced staff and provide training for the measurement. Check or validate software to make sure it works correctly. Use rounding correctly in your calculation. Keep good records of your measurement and calculation. Write down readings at the time they are made. Keep a note of extra information that may be relevant. If past measurements are ever called into doubt, such record can be very useful. Many more good measurement practices are detailed elsewhere, for example, in the International Standard ISO 9000 series and IEC 17025. General requirement for the competence of testing and calibration laboratories. Uses of calculators. When using calculator or computer to work out uncertainties, you need to know how to avoid mistakes when using them. The X bar key gives you the average arithmetic mean of the number you have entered into the calculated memory. Sigma n minus 1 is sometimes marks as give you the estimated standard deviation of the population based on your limited sample. In practice, any set of reading is a small sample from an infinite population of possible reading. Sigma n minus 1 is the estimate of standard deviation you should use when calculating standard uncertainty for a type B calculation as discussed previously. The calculator may also have a key marked sigma n. You should not normally use sigma n. For your estimate of uncertainty, sigma n gives the standard deviation of sample itself and does not give the estimate for the larger population you are trying to characterize. For a very large number of readings, sigma n is very close to sigma n minus 1. But in real measurement situation, with moderate number of readings, you should not use sigma n. Calculator and software. Calculator can make mistakes. In particular, they are sometimes give unexpected results when dealing with the long numbers. For example, some calculation 0.00000060 to 0.602, this will be 0 exactly. When the correct answer is 0.1204, of course, this would be better expressed as 2 into 10 to the power 7 multiplied by 2 into 10 to the power 7. This will be 4 into 10 to the power minus 14. Even computer can suffer from this type form of rounding error. To identify this problem, spreadsheet software should be checked by running through a typical calculation by hand and to make sure both methods agree. To avoid these problems, rounding, it is good practice to work with transform number in your calculation. This is sometimes called scaling or coding data. Scaling. Example 4 shows how to perform scaling to avoid the software and calculator error and make arithmetic easier if you are working with calculator. Suppose find the average of each number 1.0003 and 1.000006 and other is Working in whole number, you can use the 3, 6 and 12. This is average of this is 7 and then reduce the average is this 1.0 and in last 7. So step by step, you subtract the 1 from the each, you will get 0.3, 6 and 12 and multiply by 10 to the power 8, then you will get 3, 6 and 12. Then taking average 7. Finally, when 7 divided by this 10 to the power 8, we get this. So this will be correct. Scaling to calculate the estimated standard deviation, average is 7. We will go to 7 is 6, less than 1, and less than 4, 5. So we take the differences from the 7 and inspiring them and finally divided by n minus 1. So these are three values divided by u. Then we take square. This will be 4, 6. Finally, the standard deviation is 0.0000446. Rounding calculator and spreadsheets can give the answer to many decimal places. And these are and there are some recommended practices for rounding the result. Use the meaning degree of rounding in calculation. The uncertainty in the measurement result may define how many decimal places you should report. For example, if uncertainty in your result is in the first decimal place, then the measurement result should probably also be stated to one decimal place. So, for example, 20.1 centimeter plus minus 0.2 centimeter. Make the calculation to the least to at least one more significant figure than you eventually required. Be aware of how many significant figure needed to use when multiplying or dividing or carrying out one more complex calculation. Rounding the values should be carried out only at the end of calculation to avoid the rounding. For example, 2.346 is round up 2.35 at early stage in the calculation. It could later be rounded up 2.4, but 2.346 is due to throughout a calculation. It could be correctly rounded to 2.3 at final stage. Although results are finally rounded either up or down depending on which the nearest figure. The rule for the rounding uncertainty is different. The final uncertainty is rounded up to next largest figure, no, not down. Word of warning: uncertainty analysis is an evolving subject area. So there have been subtle changes in the approach. So extra rules, if anyone uses statistics on a small set of data about the if one component of uncertainty is much bigger than all the other, if some input to the calculation are correlated, if spread or distribution is unusually safe, if uncertainty is not a for a single result but befitting a curve or line. Now, concluding remark, due to the legal regulations to which the verification is subjected, the user of a verified instrument may may assume that during the validity period, the instrument will indicate values within the maximum permissible errors in service. This is the case even if measurement uncertainty are taken into consideration, so that there is no shared risk. The environmental conditions during use are the same as those prevailing During the verification, the values can be expected to be even better than the maximum permissible error on verification. Probability 95%. But in the worst case, the small proportion of the instrument, they may be 1.33 times the maximum permissible error on verification. This value is significant for the user of an instrument. This is outside the regulatory sphere, but who still has to prove the traceability to national standard. These are some differences and again reports by the research image. He wrote scientific knowledge is the body of the statement of varying degree of certainty, some most unsure, some nearly sure, but not absolutely certain. The similar way, Walter Levin said, any measurement that you make without the knowledge of its uncertainty is completely meaningless. So thank you, one and all. हेलो हाँ जी सर ये पूरा हो गया
अभी तो है
Am I audible?
Sir,
Yes,
Audible?
yes,
sir,
Ashutosh ji.
yes sir. आवाज नहीं आ रही आपकी
Okay. संतोष जी
Yes, sir. ये आवाज आ रही है आपकी सर
हेलो
क्या सर अच्छा फोटो सर का नंबर
हाँ दे देना सर को भेज देंगे
हाँ
हेलो।
यस सर, आपकी
हेलो।
आवाज आ रही है सर। अग्रवाल सर, आपकी आवाज आ रही है।
Oh, thank you very much. I would like to thank Dera Singh sir, lecturer, and all the participants. Santosh ji, have you taken the photographs?
Little bit, but some of the users are not switch on the video.
Kindly make all the participants the panelists. Can we close this meeting?
Sir,
Hey, Sanjay भैया,
yes sir.
टीवी ऑन है।
There?
क्वेश्चन पूछ रहा होगा
सेटिंग
और जो
Can we close this meeting?
नहीं दिया है।
বিবেকানন্দ কুমার রয়েছে। এই তুমি লিখে লিখে দাও, গুড লেকচার, থ্যাংক ইউ।